Good day, everyone. Welcome to our lectures in Electric Circuits Theory 2. Today, we're going to discuss AC power analysis. And in this topic, we're going to know the difference between instantaneous power and average power. We're going to talk about AC version of maximum power transfer theorem and learn about the concept of effective and RMS values, learn about to complex power, apparent power, and power factor. We're going to understand the principle of conservation of AC power. And the last part is we're going to learn about the power factor correction. Okay, so instantaneous power is defined as the power at any instant of time. And since we are in AC power analysis, our power is in terms of uh, AC also, or in terms of time domain. Notice that our sources for voltage and current, it is given in time domain and it is in sine or cosine function. So if we graph this cosine function or the voltage function, this is the graph for voltage function. Okay, and for current in terms of cosine function, this is the graph. If we take the product of the two functions, then this will be the resulting graph, which is the power. Okay, the resulting graph of the product of two uh, equation or the function. Okay, so this product is what we call our instantaneous AC power, and this is derived according to the trigonometric quantity as if we take the uh, cosine of two function. For example, we have cosine A multiplied by cosine B. That will result to we have 1/2 of cosine cosine of uh, cosine of A minus B plus cosine of A plus B. Okay, so this is the trigonometric identity for this product of two cosine function. So that's why we have this equation. The derivation of this uh, product uh, can be seen on the book of study. Okay, next we have um, the instantaneous AC power consists of uh, two parts. We have here the constant part and we have here the part which is a function of time. And this constant part um, is what we call the real. Usually this is termed as the real, or this is our constant power. Okay, this is our constant power. And this part here is what we call your sinusoidal power, since it has its own frequency. Here we have the frequency omega. Okay, omega is defined as 2 pi f. So we have the frequency. So frequency usually given in 60 hertz. Okay, 60 hertz seconds. Or sometimes it's given in 50 hertz. Okay, so next we have the graph for instantaneous power and the average power. So here we have the graph for instantaneous power, if we multiply the voltage and the current function, so the average power is the power in between the instantaneous power, okay, or it is in the formula 1/2 the V maximum or the Vn, or this is your Pm, yeah, okay. This is also your negative Pm, okay, wherein you have your V maximum in your sinusoidal form, have your V maximum, okay, and then this is your V negative of Vm, okay. So this is the formula for average power. Okay. So here we have um, the sum of uh, instantaneous power is actually we have your P1 and P2, or P1 is your average power. Here is your sinusoidal power. Okay. So in average power, we can actually derive that one. So if you take the integral of the instantaneous power from 0 to t, or the one cycle, or the one period over the one period, the resulting equation for that is our average power. Okay, so this is the average power equation taken from the integration of instantaneous power, and that is similar also to determining the real part of the apparent power. Apparent power actually is given by S equals V and I conjugate. Okay, so the real part of that is your average power. Okay, actually our apparent power is also given in P plus JQ, where your P is your real part, real power, and the imaginary part is your, this is your reactive power. Okay, so that is why we can determine also for average power by taking the real part of this apparent power. So from that we can also write average power in terms of angle, and if we're going to determine for the average power of resistor, we can make use of this formula in terms of, this one is in terms of complex. So take note, for average power, P is not time dependent. The theta, or the angle of the voltage, is the same or equal to the angle of our current. So when that will be, that angle is equals, the load is purely resistive. Okay? So for purely resistive load case, that consists of usually our lamp or heaters. So these are the example of resistive load. And when your angle B minus angle of your current is equal to positive or 90, that is, that load is what we call purely reactive load case. So if it is positive, so our load case is inductive, and if it is negative 90, our load is capacitive. Uh, or for elements that absorb or store energy, okay, our average power is equal to zero. Usually, our inductor and capacitor has no average power. Take for example, we have to calculate the instantaneous power and average power absorbed by a passive linear network. We have here equation for our voltage, and we have sine function for current. Now, to apply the formula, we have to convert everything into cosine form. Okay, so in this case, the current is since current is given in sine form, so we have to convert this first into cosine equation or cosine function. And to do that, we can make use of the graphical conversion of cosine and sine function. So here we have positive cosine omega t. Here we have positive sine omega t. And going down is actually 90 degrees negative if it is in clockwise direction. Okay. Cosine omega t is actually, if we go down from cosine to sine omega t, we have cosine omega t is equivalent to sine omega t minus is clockwise direction. It is in clockwise direction, we have minus 90 degrees. Okay, so we have here 15 cosine of 10t plus 60 degrees. Then we have to subtract 90 degrees so that it will become cosine function. So you have 90 degrees, and this will 15 cosine of 10t minus 30 degrees. So here we have your theta v is equivalent to this, and for theta at 30. The maximum values are Vm is 80 degrees, Im is 50. Therefore, Vm Im is equivalent to around 600. This one here is uh, 20 minus 30, so this will become 50. Okay? 20 minus 30 is 50. If we're going to compute that one, you have cosine of 50 is 0.64 multiplied by 600, 385. Here we have 20 minus 30 negative 10. So this is the instantaneous power of this given voltage and current. And the average power is in this formula. So in that case, we have 355.7 watts.
Okay, so another example for average power, we have here find the average power absorbed by the resistor, the inductor, and find also the average power supplied by the source. Okay, so to find for the average power, we have to compute first for the voltage and the current of that element. Okay, so first is since this circuit is a series circuit, so we need to compute first for the current flowing through that circuit. Okay, so by Ohm's law, we can actually compute for current have voltage divided by the total impedance of the circuit. Okay, so we have here the voltage, or using KVL, we have 8 angle 45 divided by the impedance 3 plus J. So we have the current 2.53 angle 26.57 degrees. To compute for the voltage of the resistor, we just simply multiply 3 ohms by the current obtained. You have 3 times 2.53 is 7.59 angle 26.57 degrees. And if we apply the formula for average power, since this is a resistor, so the angle must be uh, the difference between the angle of the voltage and the angle of current should be equal to 0. So we have now 1/2 of the V max, or the voltage maximum, and the IM maximum, which is this one, and for current we have 2.53. So we have the average power of resistor 9.6 watts. For the inductor, to find for the voltage of the inductor, we just simply multiply the J, this one, multiplied by the current, 2.53. So will the answer would be 2.53 angle 116.57. Okay. So for average power, we make use of the formula Im and Vm, and the difference of the angle between voltage and current is 90. So therefore cosine 90 is 0. So therefore our average power is 0 for the inductor. For average power supplied, you have 1/2 of Vm. This is your Vm, and the current Im, cosine of the angle of the voltage is 45 minus the angle of current. So uh, this gives us 9.6 watts for the average power supplied by the sources. So I have here also the problems. Calculate the average power supplied by each of the size element, 5 elements in the circuit given. So consider the circuit below. We have here the element, um, 40 volts and negative J20 volt, J4 ohms, 8 ohms, and negative J2 ohms. Okay, to find for the average power, we need to compute for the current and the voltage of for each individual elements. And to do that, we can apply mesh analysis or nodal analysis in the circuit. So if we apply for mesh analysis, for mesh 1, okay, we have here negative J40 volts and plus 8 minus J2I1, okay, um, negative plus negative J2I2. So this gives us the equation 1. And for mesh 2, we have negative J20 plus J4 plus minus J2I2 plus negative J2I1. So if we simplify that one, we have our second equation. So you can apply matrix form or by substitution or elimination method, and this gives us the current I1, which is 5 angle 53.14 degrees. For I2 we have 13.6 angle 17.11 degrees. So to compute for the average power, 1 half Vm Im, okay, cosine theta V minus theta I. We need to compute also for the uh, voltages, okay, voltages. We have for 40 voltage source, we have 40 angle 0 degrees times the current flowing through that element, and if you substitute that to the formula, this gives us the average power negative 60 watts. For the 20 volts voltage source, we have 20 angle 90 degrees, and for current 36.6 angle 17.11 degrees. Okay, so substituting to that formula, this gives us negative 40 watts. For the resistor, we will compute for the voltage. The voltage is 8 times the current flowing through that element. This is 40 volts. And since for the resistive load, the theta V minus theta I is equal to 0. Okay, that is why if we substitute the values into that equation, this gives us 100 watts. For inductor and capacitor, the average power is equal to 0 since theta V minus theta I is equal to 90 degrees. So we have here the maximum average power transfer for AC analysis. Finding the maximum average power which can be transferred from a linear circuit to a load connected uh, in that circuit. So maximum average power transfer can be applied also for AC analysis. So we have to determine for the Thevenin voltage and Thevenin impedance of that circuit. So the same principle with DC analysis or in your circuit theory 1. Okay, so from that we can derive the equation for maximum average power transfer using this um, equation. So the derivation of this can be also be found in your books. So maximum average power transfer for AC analysis is equated as VTH squared all over 8 times RTH. Okay, so this is the equation for maximum average power transfer for AC analysis. So take for example, calculate the load impedance for maximum power transfer and maximum average power in this circuit. So from the concept of DC circuit, if we're going to determine for the Thevenin impedance, so we have to turn off all independent sources, and if it has dependent sources, we need to apply test voltage or test current in the circuit. So in this case, if we turn off uh, the current source 2 ampere, so we can compute now for Thevenin impedance of the circuit. So we have here the series elements in parallel with 5 ohm resistor. So the ZTH now is 3.14 plus J 0.73 ohms. Okay. To determine for maximum average power transfer, we need to compute for voltage as well. Okay, the voltage across that load. So here we will apply uh, current division because we need to compute for the voltage across 5 ohm resistor. Okay, so the voltage across 5 ohm resistor is parallel into that load. So by current division, okay, we have, if we have actually the concept for current division is if we have the current source in parallel with the elements R1 and R2. Okay, to find for I2, we need to take R1 as our numerator. So for our I2, to compute for I2, we need to take R1 all over R1 plus R2 multiplied by the current sources. So here we have the current flowing through the 5 ohm resistor. Okay, so we take this element and then multiply by the current source all over the total impedance, all over the total impedance of the circuit. So the voltage now across 5 ohm resistor is 5 times the current, which is the current I1. Okay, so the voltage is, or the VTH now is 6.25 angle minus 51.34 degrees. To find for the Z load, so here we take the reciprocal or change the sign of your ZTH. So from positive, it will become now negative. Okay, so we have now your impedance of your load. So to compute for maximum average power transfer, we have now the scalar value, or this 6.25 squared divided by 8 times the resistance of your impedance load. So in this case you have this 3.415 ohms. So this is now the value for your Pmax. Okay, this one here is R minus Jx. Okay, so for purely resistive load, okay, the maximum average power transfer uh, can be calculated by finding the power of RL when XL is equal to 0 for resistive load, only. So we will take RL instead of XL. So here, calculate the resistive load needed for maximum power transfer and a maximum average power. So first we find the ZTH and VTH across RL. Okay, so to find for ZTH, again we need to turn off all um, independent sources. We turn off this voltage source. We have uh, this element in parallel with these two elements. Okay, so we have now the ZTH is equivalent to the parallel, have here the Z1, Z2, and Z3. Okay, so ZTH now is 17.181 minus J 24.57 ohms. So to find for the uh, VTH, okay, the VTH is the voltage across your negative J3 ohms, or the voltage across uh, 90 ohms element, no? Since they are both connected in parallel. So VTH can be computed as we simply apply voltage division. Okay, so we have here the parallel, which is denoted as Z2. Okay, so by applying voltage division, so Z2 all over the total impedance of the circuit multiplied by the voltage source. So we have now the value for VTH, or the voltage across your load, or the voltage across your Z2. Okay, so to find for RL, so RL is simply from the ZTH. So if we simplify this one, this gives us 17.181 plus or minus 24.57 I. This is equivalent to, if we convert that one into polar form, we have 29.98 angle 55 point, this is actually 0.4. So RL is simply, or this is equivalent to 30. So you have 30 ohms for RL. Okay. Next is we need to compute for the current through that load. So current can be computed as VTH all over RTH plus your RL. Okay. So ZTH, this one, plus RL, which is 30 ohms. Okay. So 30 plus 17 is 47.181 minus 324. Okay, so this one now is the total current of the circuit. So to find the maximum average power absorbed by RL, we need to apply the formula I squared RL. Okay, so we simply apply the I squared R, or V squared over RL. So aside from sinusoidal signal or function, there are other form of signal, especially in DC circuit. So a periodic current in a DC value that delivers same average power to a resistor as the periodic current is what we call your root mean squared, or the effective value. So in AC circuit, we are determining the average power, and for DC circuit, we need to determine the effective or RMS value of that periodic current. And to do that, we need to apply the formula for the effective or RMS value of that signals or that functions. And we can apply the formula for average power in AC circuit. So by applying the formula for average power, we can now obtain the formula for the effective value or effective RMS power of that signals or function. So for the effective or RMS value of current, from this formula, we have the square root of the integral of the current in terms of time domain, the same for voltage and power. Okay, so therefore you have the effective power formulated as VRMS IRMS cosine of theta B minus theta I. For the resistive load, we can simply apply VRMS squared over R. So this RMS value most of the time is stated in the problem. For example, we have this periodic current or waveform of a current. So determine for the average power if the current applied is applied to a 9 ohm resistor. So we have here this waveform is usually termed as sawtooth. Okay, so at time interval 0 to 1, we have this function 40, and it changes from time interval 1 to 2 seconds. Okay, so you have 8 minus 40. To determine for the effective or RMS or the average power, we need to determine for IRMS, which can be computed as the function from 0 to 1 plus the function at 1 to 2. So from that, we have 1 over t integral from 0 to t I squared dt. So one period is from here you have 0 to 2. This is your one cycle or one period. So period is 2 seconds. So therefore you have substituting the equation, you have 40 squared, okay, integrated from time interval 0 to 1 plus uh, 8 minus 40 squared integrated from evaluated from 1 to 2. So therefore our IRMS is equivalent to 2.3 ampere. Therefore the average power can be computed as I squared RMS times R, that gives us 48 watts. So another example, you have to find the RMS value of the full wave rectified sine wave. This happens most of the time if we have our bridge rectifier. Okay, so we need to transform AC to DC. So the function for that is we have the voltage 8 sine t at interval 0 to pi. Okay, so this is your time or one period, meaning your one period is equivalent to pi or one cycle. Okay, so we will also apply the formula for effective voltage, this one here. So V squared equals 1 over T integrated from 0 to T V squared dt. So we have here the function evaluated from 0 to pi, and that gives us 5.67 volt. Okay, or the average power can be computed as 5.33 watts.